Welcome to This Explainer. Today, we're diving into something we see all the time but usually totally take for granted. I'm talking about the hidden, honestly fascinating physics of trains. We're going to explore exactly how these massive machines convert raw energy into motion. And specifically, our main focus today is zooming right in on exactly how those train wheels physically create that motion.
To really wrap our heads around this, just think about the sheer, awe-inspiring scale of rail transport for a second. We are talking about vehicles that just effortlessly carry hundreds or literally thousands of tons of weight all at once. It's an absolutely staggering amount of mass to be hauling across the country, right?
Okay, let's dive into this. How do thousands of tons move so efficiently with relatively little energy? It's kind of a core mystery, right? It totally defies our everyday experience of moving heavy stuff. Like, if you've ever tried to push a stalled car, you know how incredibly hard it is to move just 2 tons.
So, to understand this, we're going to start with Section 1, the steel-on-steel advantage.
The secret here actually lies in the brilliant simplicity of the materials themselves. Think about it. A train works by utilizing steel wheels rolling directly on steel rails. And because of the extreme hardness and smoothness of that steel, this specific combination creates very, very little friction. Now, in physics, we call this extremely low rolling resistance. It essentially acts as the ultimate mechanical solution, right? It's what allows these unimaginably heavy trains to just glide and move so efficiently. Honestly, it's the foundational reason rail transport is even possible in the first place.
Next up, we have Section 2, sourcing the power. Let's look at where all this motion actually begins. Now, what's really interesting about this slide is the sheer variety of ways trains generate the raw power needed for all that movement. We're basically looking at 3 main power sources here. Steam trains, they burn coal, wood, or oil to heat water into steam, and then that steam pushes pistons to turn the wheels. Then you've got diesel trains. They use a diesel engine to power a generator, which produces electricity for electric motors that are connected to the wheels. And then, of course, we have modern electric trains, which just bypass onboard generation entirely. They get their electricity directly from overhead wires or a third rail to turn their motors. But, and this is the key takeaway here, look at what they all have in common. Despite having completely different fuel types, they all share one ultimate, singular goal: delivering power straight to those wheels.
And that brings us to Section 3, how wheels create motion. This is the exact moment that energy finally becomes physical movement.
So let's walk through this step by step, this whole chain reaction of propulsion. Step 1, the motor. And like we said, whether that's powered by steam pistons or electricity, doesn't matter. It rotates the train's driving wheels. Step 2, the wheels grip the steel rails through friction. Now, I know what you're thinking. We literally just talked about low friction, right? But the thing is, because of the immense weight, there is just enough grip or traction right there between that heavy steel wheel and the steel rail. And then we hit Step 3. That rotational force leverages that tiny bit of rail friction to push the entire train forward. It is just such a beautiful, highly efficient transfer of energy into forward momentum.
Moving right along to Section 4, guided by the rails. Because, once you have all that forward momentum, you gotta have directional control.
And this brilliantly illustrates another entirely unique aspect of this kind of movement. Just think about your car for a second. You steer it by physically turning its wheels left to right, right? But trains, they do not steer like cars at all. The steel rails actually physically guide the wheels to keep the train on its path. Literally, the track itself does the steering. It's a huge contrast to the familiar, everyday mechanics of driving, and it's what makes the entire transit system so incredibly streamlined.
Let's see how this all builds into our final section, number 5, bringing it to a halt.
Because obviously, once you get thousands of tons moving, you eventually have to face the incredibly complex mechanics of bringing all that massive weight to a complete stop. Historically, and honestly still very commonly today, this is done through traditional braking. This is where air brakes literally press brake pads or discs directly against the wheels. So it's just using traditional mechanical friction to slow the vehicle down, fighting tooth and nail against all that massive forward momentum.
But modern engineering has actually taken this a massive step further through something called regenerative braking. This is a system in a lot of modern electric trains where the motors themselves actually act as generators, converting the train's motion back into electricity. So the crucial point is that this kinetic energy isn't just lost or burned off as heat, like it is in traditional friction braking. No way. It is captured and completely repurposed. It is a true modern engineering marvel. The very act of stopping a modern electric train actually generates power. Just think about that for a second.
Hitting the brakes on a massive 1,000-ton machine actually powers it back up, feeding electricity right back into the grid. I mean, it completely flips our whole understanding of energy consumption on its head. It really makes you wonder, if the simple act of stopping a vehicle can generate the power to make it go again, what other everyday processes are hiding massive reservoirs of untapped energy, just waiting for us to engineer a solution? Thank you so much for joining me for this explainer. Keep asking those great questions, and I'll see you next time.